Welcome to the lecture series on alkyl halides. We've been discussing the preparation of alkyl halides. This is episode 3 and the second part of alkyl halides preparation. Let us recall what we did in the preparation of alkyl halides earlier. We talked about the preparation of alkyl halides from alkanes and the mechanism of free radical formation was discussed in this preparation. The advantages and disadvantages of this method were also discussed, and then we talked about the preparation of alkyl halides from alcohols. In alcohols, we saw how the alkyl halides can be prepared using primary, secondary and tertiary alcohols. In this particular episode, we shall take up the preparation of alkyl halides from alkenes. So, from alkenes we can use halogen acids, also the halogens to prepare alkyl halides, and there is another method, we call it allylic halogenation, which is again pertaining to the use of alkenes. The mechanism of alkyl halide preparation from alkenes will also be dealt along with the methods which are listed here, and then of course we would sum up this particular episode. Let us start with the preparation of alkyl halides from alkenes using halogens or the halogen acids. So, alkenes react with halogens like chlorine and bromine, or halogen acids, hydrofluoric acid, hydrochloric acid, hydrobromic acid or hydroiodic acid to form alkyl halides by addition at room temperature. The reaction is called electrophilic addition reaction. Why we call it electrophilic addition reaction is that the addition is electrophilic in nature. The electrophile starts the reaction of addition to the alkene, and in this reaction the electrophile comes from the halogen or its acid, and the alkene double bond is the electrophilic center. So, the electrophile adds to one and the nucleophile adds to the other sp2 carbon of the alkene. This can be understood by seeing this reaction. So, we have an alkene, a double bond here, and it reacts with the hydrogen halide, or there are two parts of the reactant, that is we have a plus part that is electrophilic in nature, and we have a negative ion or the negative part of that molecule which acts as a nucleophile. So, in the first step actually the pi bond breaks and the new sigma bonds with the electrophile and the nucleophile are formed. So, the both the ions are attached to the alkene and we get the formation of alkyl halide. An example of addition of HBr to ethylene to give bromoethane or ethyl bromide can be seen here. Ethylene reacts with hydrogen bromide to give bromoethane, and as you have seen here that this double bond of course becomes a single bond, and there are two sigma bonds in place of a pi bond which get formed during this reaction. But what happens when the alkene is asymmetric? What do we mean by this is, this ethylene is a symmetric molecules, which means that we have two hydrogen atoms here, two hydrogen atoms the other side, and both the hydrogen atoms are similar. So, whether H gets added to this carbon or this carbon of the molecule from HBr does not make any difference. When the alkene is asymmetric, for example, addition of HBr to propene may form 1 or 2 bromopropane. The hydrogen of the halogen acid may go to either of the sp2 carbons. These are the two sp2 carbons present in this alkene, and this is the hydrogen bromide. So, one possibility is that 2 bromopropane gets formed, bromine comes to the second carbon, and the other possibility is that bromine goes to the first carbon itself. Addition of HBr to propane is said to be regioselective. That is, one direction of bond breaking and bond making is preferred over the other direction. We can put it in other words also, formation of one product dominates over the other, and the hydrogen of the halogen acid may go to either of the sp2 carbons. You can recall the Markovnikov's rule here. This reaction is also governed by Markovnikov's rule, which was given by the scientist Vladimir Markovnikov. This rule states that during the addition of HX to an alkene, hydrogen adds to the double bonded carbon that has the greater number of hydrogens already bonded to it. So, if we look into it, we will be able to rationalize this rule. We have this substituted propene with butene with us, and Hi is the hydrogen halide we are using. So, this hydrogen will go to the carbon which already has more number of hydrogen atoms. So, this CH2 is the one which has 2 hydrogen atoms in it. Hydrogen will get attached to this hydrogen, and the iodine atom will go to the next carbon which had lesser number of hydrogen atoms. So, if we look into the mechanism of this particular reaction, we will realize that in the first step of the reaction, electrophilic addition of a proton by transfer of a proton from HBr to 2-butene takes place, and then pi bond of the alkene breaks and its electron pair forms a new covalent bond with the hydrogen atom of HBr. The polar covalent bond in HBr breaks and its electron pair moves to bromine to form a bromide ion. Let us look into this. The first step leads to the formation of an organic cation and a bromide ion. So, we have this nucleophile here, and the H of HBr acts as an electrophile. We know that this double bond is the electron center. Therefore, this electron center picks up this proton without its electrons, and the bromine of this HBr goes along with the shared pair of electron. As a result, it gives us a bromide ion, and a positive ion, a secondary carbocation, is created for the alkene which was used. This is the first step. In the second step, making of a new bond between a nucleophile and an electrophile takes place. So, we can see that this bromide ion is now a nucleophile, and we have a positive center here. You will again recall that the nucleophile is the one which is nucleus loving, that is the one which will go to a positive center. Reaction of the secondary butyl cation, which is an electrophile, with bromide ion nucleophile leads to the formation of 2-bromobutane. And what is the explanation we give for the preferred formation or the Markovnikov addition of the hydrogen halide to alkene? This can be explained on the basis of the stability of carbocation which is formed in the first step of the reaction. According to the experimental evidence, the stability and activation energy of formation of carbocations varies in the following order. Tertiary carbocation is more stable as compared to secondary carbocation, which is more stable as compared to the primary carbocation. The two effects, that is inductive and hyperconjugation, explain the stability of the carbocation. You would recall that inductive effect is the one which is observed when there is sigma bond in the molecule and it travels through sigma bond, whereas hyperconjugation is the no bond resonance effect, which is responsible for the stability of many molecules. So, the stability of carbocation can be shown for methyl, primary, secondary and tertiary, following the order, that methyl being the least stable, then is the primary and then is the secondary. Finally, the tertiary carbocation is the most stable one. So, sometimes what happens that when HBr is added to alkenes, we do not observe the product which we saw earlier, and we say that this follows a non or anti-Markovnikov addition. It is observed only in the presence of peroxides or other sources of radicals. This means that there should be a peroxide which should be able to generate a radical moiety in the reaction mixture. In the absence of radicals, usual Markovnikov product is obtained. So, this anti-Markovnikov addition is observed only with HBr and not HCl or HI. So, if we look into this example, this is 2-methyl propene which reacts with HBr in the absence of peroxide. There is no peroxide present and we get the usual Markovnikov product. That is, the hydrogen of the hydrogen halide has gone to the carbon which had more number of hydrogen atoms. So, to this CH2 hydrogen has gone, as a result it has become CH3 and the other side of the carbon gets the bromine atom. This is the Markovnikov addition. In case of a non or an anti-Markovnikov addition, we get the substitution of bromine atom at the end carbon, that is the CH2 carbon which had lesser number of hydrogen atoms, and the formation of 1-bromo 2-methyl propene is there. So, let us see how is it explained. The anti-Markovnikov addition actually follows chain radical mechanism. So, where you are familiar that the first process in this particular mechanism is chain initiation, under which we have the first step where homolytic cleavage of dialkyl peroxide is induced by light or heat to give 2 alkoxy radicals. So, this is triggering of the radical formation, and then comes the second step of this reaction where alkoxy radical reacts with HBr by hydrogen abstraction to give alcohol and bromine radical. So, this alkoxy radical will take this proton, this HBr also undergoes a homolytic fission. As a result, we get the formation of bromide radical, which is the one required for the reaction further. So, chain propagation is the second process of this mechanism, where the third step of the reaction takes place. Bromine radical adds to the carbon-carbon double bond regioselectively to give the more substituted and more stable carbon radical. So, here we have to see now which radical is more stable, because again we have a possibility of formation of a primary and a tertiary radical. In chain propagation, again in the fourth step, the carbon radical reacts with a molecule of HBr to give the bromoalkane and generates a new bromine radical. At the chain termination step, combination of 2 bromine radicals takes place, or also combination of a carbon radical with a bromine radical takes place. And in the chain termination step, as we saw earlier also, the radicals get quenched or the radicals get destructed. Similar to hydrogen halides, we can make the halogen molecules also react with alkenes, which undergo again an addition reaction at room temperature and form the alkyl halide. So, there is formation of 2 new carbon halogen bonds, because in the previous method we had HBr, here we have 2 bromine atoms. Both of these get attached to 2 carbon atoms and give an addition product. The reaction may be carried out either with the pure reagents or by mixing in an inert solvent such as dichloromethane. The mechanism is by electrophilic addition of bromine to double bond. So, you can see here that this is bromine molecule adding to this ethylene molecule, and here is the formation of a bromonium ion, and finally the dibromoethane molecule is generated. And if we look into its mechanism in little details, we will see that this is initiated by interaction of the pi electrons of the alkene with bromine, as is shown in this particular reaction. Formation of an intermediate with positive charge on bromine is created. So, this particular ion we call as bridged bromonium ion, the bromine with a positive charge, and with this we generate a nucleophile. So, in the next step, formation of a new bond between a nucleophile and an electrophile takes place, where attack of bromide ion, which is a nucleophile now, on carbon from the opposite to bromonium ion, that is an electrophile, takes place. So, we should observe that here the three-membered ring opens up to give the anti-product called the anti-coplanar attack. Because this is a planar molecule, there was bromonium ion and the bromide ion has attacked from the opposite side, therefore, we call it as anti-coplanar attack, which results into the formation of the corresponding alkyl halide. Similar to what we observed in case of alcohols, that reaction happened to be a qualitative test for differentiating between primary, secondary and tertiary alcohols. We observe that addition of a halogen molecule to an alkene also gives us a very good qualitative test, because addition of bromine to double bond finds use in the qualitative test for the double bond, and we observe that dichloromethane and bromine mixture is red in color, but alkene and dibromoalkene is colorless. So, when a mixture of bromine and alkene is added to the red solution, it turns colorless because of the formation of the dihaloalkane. Another important aspect of preparation of alkyl halides from alkenes is allylic substitution. Here you should know what is an allylic carbon. An allylic carbon is the one which is adjacent to a double bond, and here we are talking about substitution at that allylic carbon. So, alkenes react with chlorine or bromine in presence of sunlight or at high temperature to form haloalkanes by allylic substitution. So, this is propene which reacts with this halogen molecule in presence either in presence of light or very high temperature, and gives, now the double bond is intact, but the substitution has taken place on the allylic carbon. As a result, we get 3-bromopropene and not the saturated hydrocarbon, and as a result HBr gets created. So, the method to carry out allylic substitution is by using a molecule like N-bromosuccinimide in dichloromethane, which is responsible for creating a radical, so that the allylic substitution can be carried out. So, this alkene when reacts with N-bromosuccinimide, we get the allylic substitution and we get succinic acid as a result. If we look into the mechanism of allylic halogenation, we will find that it also follows a radical chain mechanism, where chain initiation is the first process of this mechanism, and the first step involves the formation of radicals from N-bromosuccinimide by light induced homolytic cleavage of the NBr bond which is present in this N-bromosuccinimide molecule. So, this is the radical which gets created. This is the one which is going to further react in chain propagation, which leads to the formation of products. So, in the second step of this reaction of a radical and a non-radical takes place to give rise to a new radical. Bromine radical abstracts an allylic hydrogen, which is the weakest CH bond also. So, easily can be removed to produce an alkyl radical. In chain propagation itself, then we have third step where the allyl radical reacts with the bromine molecule to form allyl bromide and a new bromine atom. So, this is the way the two radicals will react, give rise to allylic substitution and another bromine radical. At the stage of chain termination, the radicals as usual get destructed or quenched, and in 3 steps propagation of the chain reaction continues until termination steps produce non-radical products and stop further reaction. So, either 2 bromine radicals can combine to give a bromine molecule, there can be an allylic substitution with an alkene radical and the bromine radical, and also there is a possibility that 2 alkene radicals may combine together and give rise to a dialkene. So, this is how the chain gets terminated. So, the bromine required to react with allylic radical is produced by the reaction of HBr, which was produced by HBr and NBS. So, N-bromosuccinimide with HBr generated this bromine, and this is the succinic acid. So, bromine which is required for the reaction is also generated by N-bromosuccinimide. So, that is how this reaction is important. The order of reactivity for allylic substitution remains more or less the same what we observed in our earlier preparation methods, that is the vinylic carbon happens to be the least reactive, then is the methyl, then is primary, and then comes the secondary radical, and then is tertiary, whereas the allylic substitution happens to be the most feasible and the allylic radical happens to be the most reactive radical out of all these which are listed here. So, let us sum up what all has been dealt in this particular session. We have talked about the preparation of alkyl halides from alkenes by addition of hydrogen halide and halogen molecule, or we have seen that allylic halogenation is another possibility in case of alkenes by which we can prepare alkyl halides, and the mechanism of addition of the hydrogen halide and hydrogen molecule shows that hydrogen halide adds by a free radical mechanism, whereas halogen molecule takes place by electrophilic addition mechanism. The allylic halogenation is also following the free radical mechanism, for which we need molecule which can initiate the formation of radicals. So, this was all about the preparation of alkyl halides using alkanes, alkenes and alcohols. In the next session of the lecture series on alkyl halides, we will discuss the properties of alkyl halides. Thank you.